The sun, our nuclear powerhouse, our star. Its light powers our world and us.
Without light, we would not be alive.
Starting deep inside the sun, we follow the brutal journey of a single tiny package of light, a photon.
The ride that any photon takes to get to my eyes when I look up at the sun is an amazing one.
From its ancient birth in the sun's core to its escape from the surface.
The light reaching me from the sun was produced before there was even human civilization. It's an incredible idea.
Join our photon on its incredible million-year journey through the most hostile environment in the solar system to bring light and life to Earth. The universe, home to billions of galaxies, each made of billions of stars. And in an unremarkable corner of our galaxy, the Milky Way, lies the sun, our closest star. A dazzling sphere of intense light, too bright for the naked eye. But strip away that glare, and the sun transforms into a giant ball of superheated gas, dominating our cosmic stage.
The sun is really the star of the show. The sun is the parent of the whole solar system. It provides its children, the planets, with everything they need. We depend on the sun for energy, for light, for warmth. We would not exist without the sun.
The sun generates heat and light, the energy source for all life on Earth.
All of the energy that my body uses, literally what I'm doing to talk to you right now, came from the sun. The sun truly is the creator of all of the life around us.
The sun is a constantly exploding nuclear bomb, violent and essential.
Our entire existence is powered by the energy emitted in those nuclear reactions in the sun. We are here because of the light from the sun. We are here because of those nuclear reactions, and no aspect of our existence could persist if it wasn't there.
Light is one of the basic building blocks of the universe.
I find light to be probably the most amazing thing in the universe. It's so important in everything. I mean, it's everything, it's everywhere. So it's such a fundamental part of everything that exists.
Fundamental and fast. The fastest thing in the cosmos. Traveling at 186,000 miles per second.
The sun's about 93 million miles away from us. So going at 186,000 miles per second, that's about 8 minutes.
But those 8 minutes are just the brief last leg of its incredible journey. It may have taken the light as much as 1 million years to escape from the sun's raging interior. Which means the light we're seeing right now was created long before our ancestors left the plains of Africa.
When I first learned this fact, I was already a practicing scientist. I'd never really thought about that. And on first glance, it just blew me away.
Right now, the light reaching me from the sun was produced before there was even human civilization. And yet the minute it gets to the surface of the sun, it races away and is here 8 minutes after that. It's an incredible idea.
The ride that any photon takes to get to my eyes when I look up at the sun is an amazing one.
That ride starts deep in the belly of our star. If we could open up the sun, we we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge. They're both positively charged. They want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse. And that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together, and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
Each collision creates a tiny burst of energy, a packet of light, impossibly small and incredibly powerful. Somehow, our photon will deliver its energy to Earth, where it will power the planet and make life possible. But right now, it's nothing like the light we see. It has massive amounts of energy, and it's deadly. The light we see from our star is old. Much older than the 8 minutes it takes to get from the sun to Earth. That short leap across space is the end of a long, hard journey that starts deep inside our sun.
When we look at the sun, we say, how beautiful, how elegant, and how simple. Light is formed in the sun, and it shines and lights up our world. Well, not so fast. It's actually very complex.
The journey starts in the immense heat of the sun's core. Crushed together by the sun's enormous gravity, atoms smash into each other and fuse, releasing a tiny packet of energy, photon of light. Far smaller than an atom, with no mass. Photons travel faster than anything else, and they never stop moving. Photons don't just come from the core of stars.
So where does light come from? The short answer is matter makes it. And the amount of light that it creates depends on its temperature.
Every piece of matter in the universe above absolute 0 degrees produces light, including humans.
We humans are emitting light all the time because we're alive, we're warm, we're not at a 0 temperature. So in fact, we are emitting infrared radiation, often called heat radiation. But all matter emits light.
Even someone as cool as me, I'm creating light right now.
The light we see can be split into the colors of the rainbow. Each color is photons of light with slightly different amounts of energy. And what we can see is only a fraction of the light spectrum.
Our eyes are actually imperfect detectors. We know about visible light, the type of light that our eyes are sensitive to, but that's only a small range of energies. Light comes at higher and lower energies than we can detect.
Using special cameras, we can see the infrared light that humans emit. This infrared light has less energy than the visible light we see. Some light is too energetic to see, like ultraviolet, X-rays, and gamma rays. The vast, hot sun generates all forms of light. But in the nuclear furnace of the sun's core, every photon starts out as a gamma ray, the most energetic form of light in the universe.
And when a nuclear reaction happens, it emits an amazing amount of energy. Energy much, much bigger than visible light. Gamma rays, we call them. Literally almost 1,000,000 times, or at least 10,000 times the energy of the light we see.
Gamma rays can transform and even kill.
There's a reason why gamma rays turned Bruce Banner into the Hulk. Gamma rays are a very dangerous form of light. They can travel into your body, and when they interact with the matter, they can break apart atoms.
Fortunately for us, our gamma ray photon can't head straight out of the sun.
If the sun were not this hot ball of gas, then upon being created, a photon would immediately escape from the sun, and it would be a gamma ray photon, a very energetic photon, not very good for life on Earth.
After its birth as a gamma ray, our photon starts to race out from the sun's core at the speed of light. But it encounters an obstacle course of epic proportions. A journey that should take seconds slows to a cosmic crawl.
It takes, on average, about 100,000 years for a photon to make it from the middle of the sun where it was created to the outermost edge where it gets emitted into space. 100,000 years. If it had traveled in a straight line unimpeded, it would have taken 2 seconds.
What could possibly slow a photon moving at the speed of light? Something slams on the brakes. Huge, hot, dense, so powerful, it doesn't just slow light, it transforms it. In the sun's core, nuclear fusion releases a tiny bundle of energy, a photon of light. It races outwards at 186,000 miles per second. At that speed, it should take 2 seconds to travel through the sun's interior to the surface. But something turns seconds into an eternity.
The sun is so dense that to get through all of the different layers of gas, this poor little piece of light takes hundreds of thousands, if not 1,000,000 years to get to the surface.
So when you're looking at the sun, you're looking at the light emitted from reactions 1,000,000 years ago.
Our newborn photon leaves the core at the speed of light, only to run smack into a dense soup of hydrogen atoms. A photon's nightmare that stretches for over 400,000 miles.
If you're a photon born in the center of the sun, you have a heck of a journey ahead of you.
It's actually pretty hard for light generated in the core of the sun to get out because there's a lot of sun in the way and it's extremely dense.
The radiation zone surrounds the core of the sun. The zone is made of hydrogen gas, but not gas as we think of it. The sheer weight of all the material above compresses the radiation zone till it's denser than lead and nearly impossible to pass through.
A photon produced in the center of the sun knows where it wants to go. It wants to go to the edge, where it's cool, and it wants to get out. But it's got 400,000 miles of all these opaque gases blocking its way.
These gases aren't just dense, they're hot. Superheated to over 12.5 million degrees Fahrenheit. The gas in the radiation zone is transformed into what scientists call plasma. Plasma is the fourth state of matter. Atoms in normal matter have a nucleus with orbiting electrons. In plasma, the atoms have been torn apart and the electrons ripped away.
Here on Earth, we're familiar with the three main states of matter that we're taught in school: solids, liquids, and gases. You know, we have the atmosphere as a gas, the oceans are water, the ground that I stand on is solid. But in fact, most of the universe, including stars, consists of plasma.
Compared to the rest of the universe, Earth is a calm place. Most of the time, it's not hot or violent enough here to create plasma. The best place to witness the power of plasma on Earth is inside a lightning strike. Temperatures inside a bolt can reach 53,000 degrees Fahrenheit, enough to momentarily rip a few atoms apart. The plasma lasts an instant. Then the electrons rebind and it's gone. But in our massive sun, the plasma lasts for billions of years and makes up the entire 200,000-mile deep radiation zone. Worse for our photon, the plasma is electrically charged, forming a cosmic trap.
And a plasma is opaque to radiation because light interacts much more strongly with electronically charged objects than with neutral objects. So when you have a neutral atom, light in general can pass by. But when you've separated the charges and you have positive and negative charges located everywhere, the light can't make it through.
Our photon, in the form of a gamma ray, has entered the radiation zone and smashed into a charged plasma particle. For a fraction of a second, the particle absorbs the photon, then spits it back out, and the photon collides with another particle.
Every time it goes a little bit of a distance, it basically slams into an atom, is absorbed, and re-emitted in some random direction. So instead of just flying out, it's bouncing around countless times until finally it reaches the edge of the star.
It's an atomic game of basketball, with a court representing the radiation zone. The players stand in for the particles in the plasma, and the ball is the photon.
So the basketball is being thrown from one player to another, seemingly randomly. It's not making a lot of progress down the court, but it is gradually making progress. Gradually over time, it is going from the hotter parts of the core outward toward cooler temperatures. That's where it wants to get. It's a random-looking process, but it's directed in a certain direction with time.
The photon wants to go straight up the court, its quickest route, but is bounced and thrown around the radiation zone, slowing to a crawl. This bruising process transforms the photon.
When a photon, a little packet of light, is created in the center of the star, it's actually a gamma ray, super high energy bit of light. And it can't go very far because as soon as it does, boom, it hits another atom and gets absorbed. Every time it does this, it loses a little bit of that energy.
Over several 100,000 years, sometimes even 1 million, the photon keeps bouncing through the dense radiation zone. Each collision saps a tiny bit of energy, transforming it from a lethal gamma-ray photon to a lower energy X-ray. Nearly 1 million years after its creation in the core, the photon has made it through the radiation zone. But its quest to escape is not over yet. It's about to hitch a wild ride on the sun's ferocious internal roller coaster. A place so violent, it makes the sun roar. A photon, nature's energy delivery system, has spent up to 1 million years in the maze of the sun's interior on its journey toward the Earth. The photon has fought its way through 3/4 of the sun's radius. Battered and sapped of energy, it has morphed from a deadly gamma ray to an X-ray. But now it enters the mysterious, boiling layer of the sun, the convection zone. The convection zone lies between the radiation zone and the sun's surface and is 125,000 miles deep. We can't see the convection zone directly. This region of the sun is still opaque to our telescopes, but we can hear it. NASA's Solar Dynamics Observatory listens to the sun. The sound it picks up is too deep for humans to hear. But if you speed up 40 days recording into a few seconds, this is what you get. It's the sound of chaos. Since we can't see into the sun, its sound is vital to scientists. When a gun fires, the bullet rushes out and smashes into air, creating waves of turbulence. When we hear the gun firing, these waves vibrate our eardrums. What we see here is sound. The sun works the same way, on a much larger scale.
When we see these waves moving across, what we're looking at is when material moves up from inside the sun and it makes noise. It's just like ran into a surface. It just ran into a wall and it generates sound, and we see that sound moving all around the sun.
Sound waves crashing through the plasma create ripples in the sun's surface.
And all we see are these ripples. Those are the actual sound waves of the sun. And they move around the entire sun. They move down inside the sun. They move back up to the surface.
By tracking the sound, scientists can see the invisible. They pick up sound waves smashing against the sun's surface and resonating throughout the solar interior, revealing a violent, boiling convection zone.
The sun can be said to be ringing. You have this hot gas rising, you have cool gas falling, you have all this turbulence, you have so much action going on that it causes the sun to ring.
Columns of gases rise and fall, churned by heat from below.
If you look at water boiling, bubbles of gas or water are rising up because they're hot, and then they cool off, and then they sink back down. And if you look at a pot of boiling water, that's the same phenomena that's going on the sun, but with hot plasma instead of water.
At the bottom of the convection zone, photons smash into atoms in the plasma, heating them to a boil. But this time, the photons are absorbed by the atoms. The hot atoms ride the boiling current to the top, dragging the photons with them.
So it's almost like this conveyor belt of material. Photons are actually hitchhiking a ride on the atoms that are traveling upward through this heat transfer. So it's a much easier ride in the convection layer than it is in the radiation zone.
It's as if our photon were now in the hands of a single player making a fast break.
In the convection layer, it's a direct path. One player can actually hold on to this basketball or photon for a lot longer in a direct path.
By not passing, the atom takes the ball quickly up the court. The photon's journey through the convection zone takes just 1 week. But in that time, the photon is transformed. The bottom of the convection zone is around 360,000 degrees Fahrenheit. The top, just 10,000 degrees. So, as the photon rises up, it cools, losing energy, changing from an energetic X-ray to visible light.
So it starts as a high-energy X-ray at the bottom of the convection zone, moves its way up, it loses a little bit of that energy. By the time it leaves there, it's closer to the kind of light that we see, which is visible light.
At the top of the convection zone, the atom releases the photon, which shoots out as visible light. This cools the atoms, which fall back down to absorb more photons, heat up, and rise again. The photon is now just below the sun's surface. But the churning convection zone unleashes another force. A force that powers huge storms, detonates bombs, and threatens to stop light's escape. In the sun's core, nuclear fusion has created a photon, a packet of light. It has battled through the radiation zone, been dragged up through the convection zone on columns of hot plasma, hurtling towards its escape. On this million-year journey, the photon has changed from an invisible, deadly gamma ray to the kind of life-giving light we see here on Earth. Finally, it has reached the surface. The visible shell of the sun, the photosphere.
The photosphere, which is basically the visible part of the sun, or the surface, is what we see when we look up at the sun. We're seeing visible light coming from that very layer, the photosphere.
The ball of blinding light we perceive hides a spectacular and savage world.
The sun from a distance looks quiet and serene, but if you take a close-up of the surface of the sun, you see that it's churning with activity.
It's beautiful and terrifying at the same time. Huge storms of material bubbling and boiling. It looks like a witch's brew, except the bubbles in the witch's brew are larger than the size of the Earth.
The surface of the sun is a turbulent barrier. And once again, our photon gets taken hostage. At Kitt Peak Observatory in Arizona, solar astronomer Matt Penn studies this solar surface to discover how photons of light get trapped.
There's a bunch of theories today, but hopefully we'll get some data.
Using the McNath-Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun. But they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space. And so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth. The magnetism that generates these sunspots forms field lines covering the sun. On our solid Earth, the whole planet rotates together, including its magnetic field. But the sun is a big ball of gas, and the same rules don't apply.
You see, there's nothing solid about the sun. It's a big ball of gas. It turns on its axis, but the equator rotates faster than the poles. The sun twists itself up, and the magnetic field twists with it.
It rotates faster at the equator than at the poles, twisting and tangling its magnetic field with each rotation. The result? Magnetic mayhem.
So when these fields emerge from the surface of the sun, they have all this stored energy in them. They're like all twisted and knotted, like a rubber band that you just twist and knot, with all this energy in it. If you ever twist and twist and twist a rubber band and pull it straight, you can tell, you can feel that tension in it.
Where the magnetic lines twist, flows of plasma containing our photon can't reach the surface.
So what happens is you have these packets of gas which reach the surface, cool off, but are trapped right there by the magnetism.
A patch of the sun goes dark where light can't escape. A sunspot is born. But in that tangle of magnetic lines, something eventually has to snap.
The magnetic fields are very unhappy. They don't like the state that they're in, and all they want to do is unravel.
Huge loops of magnetic energy arc out over the sunspots. Twisted and unstable, desperate to spew their energy, they create a magnetic bomb primed to explode.
And so if one magnetic field with stored energy sees another magnetic field, those two look at each other and say, hey, if we connect, we can get rid of a lot of energy. They do so. They reconnect. Pow!
It's a huge explosion. We call it a solar flare.
And this can be equivalent to millions of nuclear weapons exploding simultaneously.
Solar flares erupt outwards into space at up to 4.5 million miles an hour, releasing massive amounts of energy.
Magnetic fields are throwing plasma from the surface of the sun. Suddenly, there's a large outpouring of light.
After nearly 1 million years, our packet of light finally makes its escape. It's free, catapulting out along with trillions of other photons. But their journey is far from over. Most hurtle onwards to the far reaches of the cosmos, to strange new worlds. After a nearly million-year journey through the most hostile environment in the solar system, tiny parcels of light, photons, finally burst from the sun's surface.
They're free. They basically are free to leave this arduous journey that they've been on in the sun, and then they fly out at the speed of light. So it's kind of a breaking out of prison type of feeling for those poor photons.
They speed out into empty space at 186,000 miles per second. And just 8.3 minutes after it leaves the sun, our photon reaches Earth.
The next time you look at a star in the sky, you might consider the amazing journey the photons have taken on their way to reaching your eye. They were created by nuclear reactions deep in the core of the stars. And then they bounced around and got degraded into lower energy photons. And then in the convective zone, they were carried by mass motions of gas. And finally, at the edge, they were set free. And they traveled unimpeded and finally reached your eyes.
Our photon finally arrives, smashes into a leaf, and passes on its energy. This is photosynthesis, the fundamental link in our food chain. Finally, carrying energy born inside the sun's core, our photon and billions like it ignite the primal fires of life on our planet. The sun's light creates our fuel, drives our weather, churns our seas. Every single day, enough photons hit the Earth to power our civilization for 27 years. The sun's light is more than just warmth and heat. It provides everything we need to survive. Without light, we are nothing.
All of the energy that powers our biology, the thing that makes our planet warm, that makes life possible, that all comes from the sun.
Trillions of photons hit the Earth every second, each delivering life-giving energy. But for the unimaginable number who pass us by, the journey is far from over. Around 80 minutes after leaving the sun, they reach Saturn. After 4 hours, Neptune.
Once a photon leaves the surface of the sun, it's free to travel as far as it can, and as far as it can be literally across the universe, billions of light years away.
They shoot past the outer reaches of our solar system in just 18 hours. Here, the sun is a dim speck in the distance. But the photons keep on going, out into deep space. In 1,200 years, some of the photons reach the red dwarf star system, Kepler-62, a solar system with potentially habitable Earth-like planets. In our galaxy, there are billions of Earth-like planets. If there is life out there, can it see the light from our sun?
If aliens exist out there, they could easily see the light from our sun. If they're sufficiently nearby, the sun might be a naked eye star in their sky. Or with telescopes, they would be able to detect the sun even from vastly greater distances. So there's a distinct possibility that aliens are studying our sun right now without realizing that we're here trying to study the universe as well.
Hurtling on, the photons pass the Horsehead Nebula in 1,500 years, and the pillars of creation in 7,000. At these distances, the light from our star is too small to be seen with the naked eye, but it would be visible with a powerful telescope.
And with the biggest telescopes that we can create here on Earth or in space, we can actually see the light from stars at the other end of the universe, over 10 billion light years away. And so the light from our sun is traveling across the universe.
So the light from our sun, the light from the Earth, travels essentially forever. The next time you're out under a clear sky and you look up, you might want to wave because somebody out there might be able to see you and wave back.
Our tiny star is visible across the universe if someone is looking.
There isn't a single place in our visible universe that you wouldn't be able to see the sun from. And maybe that's heartening. Maybe there's some evidence of our existence at the other end of the universe. Won't get there for billions of years, but at least maybe we won't be forgotten.
A journey that started deep inside the core of the sun with a photon. A million-year struggle to finally escape the sun's grip. Once free, our photon brought energy, heat, and life to our world. Light from our sun joins light from trillions of other stars, journeying through the universe, spreading energy throughout the cosmos.